The Science Basement!
Hello and welcome to the Science Basement Podcast, a podcast for people who love all things science. I am your host Sujai.
And I'm your co host, Touqeer.
Today I'm really excited to host episode 8 of season 5 because with me, as if by providence, I have the opportunity to host Dr. Shreya Trivedi. Shreya and I go way back in time. We did our masters together at the Terry School of Advanced Studies in New Delhi, India. We were the batch of 2015, so that is 10 years ago now. Anyway, I don't think I want to reveal our ages to the public. But Shreya's career has been stellar since. She did her PhD in physical geography from University of California, Los Angeles, and she graduated last year. And since then, she's a NASA postdoctoral fellow in the cryospheric lab at Goddard Space Flight Center, which is in Maryland. So, welcome, Shreya. Welcome to the Science Basement podcast. It's great to have you with us today.
Thank you, Sujai and Toki, for having me today, and thanks for a very detailed introduction. And I'm also very excited to be here today and share the kind of work I'm doing. And thanks.
Great, great.
Sujai, I graduated this year.
Oh, okay. You graduated this year. Oh,
Yeah.
yeah.
It was in
Uh,
May 2025 that I graduated from UCLA, and I started my postdoctoral program here at NASA in August of this year. So,
oh, okay, okay. Yeah, that's great. And
but
and
yeah,
so now you're on the other coast of America.
that's true. Yeah,
So
I have moved from west to east coast a completely, along with this 3 hour time zone difference. There's also a quite difference in the climate here. What at this time in LA was the forest fire season, and it was quite pleasant. It's getting quite chilly over here. So,
yeah, great. So you work in the cryospheric lab at GSFC, right?
absolutely, yes,
Yeah. So
that's
I
right.
think a good place to start would be uh, if you could give our listeners a little peep into what happens in the cryospheric lab. And I mean, from the word cryosphere, I guess most people know that it's got something to do with ice, sea ice, glaciers, ice sheets. But then you probably could elucidate further.
Yeah, of course. So, a little bit about why I went into the cryospheric lab to begin with. So,
Mm,
my career has mostly evolved around understanding the polar areas, the atmospheric part of it, the sea ice part of it. When I started my master's, it was mainly in the polar areas, and I was looking at the interactions between the polar climate and sea ice changes back in India, since you mentioned that we were working together since masters. So one of my core areas of research was looking at the interactions between sea ice and the Indian summer monsoons. And from there, I moved to UCLA for my PhD. And there too, my research background was more or less looking into the sea ice and the atmosphere interaction. But the
mm,
area where I've zoomed into and focused much in UCLA was sea ice thickness. And
mm,
the region or my study area was the Antarctic, so the Southern Ocean mainly.
right.
That's where my journey began, and I got deeply interested into the cryospheric component and the cryosphere and climate linkage. So, cryosphere, as you rightly
Mm,
described, it's more or less the science of ice or polar related stuff. So, it's mostly that, and the cryosphere lab at Goddard Space Flight Center is also highly invested to looking into the CIs, the freeboard, the satellite related, mostly ISAT 2 we'll talk in detail about it later, is their, hero product, and
Mhm.
that's mostly where they work. Most of the people at the cryosphere lab at NASA Goddard, their work is around the ISAT too. So yeah, that's like in crux what my work is. And since I mentioned that my work is about the Antarctic, what
Mhm.
makes Antarctic and the sea ice changes in the Antarctic important is because, and now also turning a lot of heads towards Antarctic, is because now in the recent years, Antarctic sea ice has hit record lows. And when I say record lows, what I
Mhm.
mean is that since 1979, when the satellite era started and the satellite data was started being collected, since then 2023 happens to be the year when we had the summer minimum in February 21, and September 10th was where the winter maximum got to its lowest values. And it's important because Antarctica was not experiencing negative trends in sea ice for a long chunk of time. And
Right.
it has started happening now. And that is the reason why people have now, started talking more and more about what's happening in the Antarctic. The Antarctic
Mhm.
ecosystems are also getting severely impacted. There was one very striking incident which took place recently, as recent as 2022-23, that there was mass drowning of several emperor penguin colonies, where chicks of penguins, they struggled to survive because the ice was too thin. It broke, and there was a massive destruction of thousands of emperor penguin chick who drowned because they couldn't develop wings to,
Yeah.
um,
I think
to
I read about this, and it was
yeah.
very well covered in like all mainstream media as well. Uh,
Exactly. So that was an eye opener, and people started thinking what exactly is happening.
hmm.
So, yeah, those are just a few incidents I could talk about, but there are many others which has basically come up as an eye opener for people and started realizing the importance of sea ice in the Antarctic.
Okay. And the ice in the other pole, that is the Arctic, that has been steadily decreasing, I guess, right? Unlike the Antarctic.
Absolutely, yes. So
Right.
in the Arctic, that's something which is established, like people know about it.
Right.
But
Right.
in the Antarctic, what's happening is that it's, what should I say? It's defying the global warming odds. Till 2014, there
Mhm.
was an increase in the Antarctic sea ice. We were looking at the positive trends in the sea ice extents in the Antarctic. So when
Right.
I say that, it's confounding for people to wrap their head around that. How is that happening? There's one pole which is completely,
Losing its
melting,
ice and
the other,
uh,
yeah, and there
mm,
is no impact on the other. How is that happening? So the one of the reasons which a lot of researchers and studies talk about is that Antarctic had a very peculiar regional heterogeneity
mhm.
in sea ice, and what that word is that uh, there are regional changes in sea ice. So, for example, the western coast of the Antarctic was losing ice,
Mhm.
and the eastern coast was increasing ice. So there was an overall positive trend in sea ice till 2014 in the Antarctic, and that was the
Okay.
reason why there was either a positive trend or there was a no change kind of situation with the sea ice in the Antarctic. So that was a happy news
Okay.
happening. The researchers were quite satisfied that comparing it with the Arctic, but things turned around after that.
Okay. Okay. Now moving to Touqeer.
Okay, well, I feel Sujai has a good knowledge regarding all of these things, but I'm very completely new to this cryosphere science. So, Shreya, can you please explain how do you figure out the ice thickness? What do satellites actually see? And also, how do you check ice thickness in winter when it's very dark and rough?
Oh, that's a very good question. And I'm glad I'm getting questions about sea ice thickness because that remains the least studied component of sea ice in both the poles. So thank you for that question, Tokir. So since I mentioned that sea ice thickness is not a very heavily studied parameter in the Arctic and the Antarctic. So, what basically is much studied or focused on is the surface parameters. So, sea ice concentration and its derivatives of sea ice extent and area. What we see on the surface is what is majorly studied. Most of the studies which you will see, these studies are based on these, surface parameters. Also, at the same time, I'm not also saying that sea ice thickness is understudied because people don't want to study it. The reason for it to be understudied is because we do not have a long term and a reliable data set, an observation data set for sea ice thickness, which can, aid researchers in making advances into this field. On the other hand, sea ice concentration, area, and extent are readily available. We have data sets about it which are more reliable, more extensively studied, and that is the reason more studies go around, using this reliable set of data. So, for the sea ice concentration, area, or extent, we have passive microwave satellites, which can easily give you a very good assessment, high resolution in terms of both space and time. A very good set of observation data sets can be provided by passive microwave satellites for the concentration, area, and extent. But when we come to thickness, we have a variety of tools which can provide us thickness values, but every tool and every component which measures the thickness has its pros and cons. Cons are more than the pros, to be honest. And that's why these data sets, they come with quite high errors. Reliability is less, but having said that, it doesn't reduce their importance.
Okay, very nice. That was a very detailed answer. So, Shreya, before I ask my question, let me add here Archimedes' principle in simple words. Anything that floats displays an amount of water equal to its weight. It means ice is lighter than water, so most of it stays below the surface and a small portion stick out. And when floating ice melt, it turns into the same amount of water that it was already holding, so the sea level almost stays the same. So now here is my real question. If melting sea ice doesn't raise sea level much, then why do we still care so much about the sea ice thickness? And also, what does thinner ice change in the ocean atmosphere system, in our weather, or even for the safety of penguins and the people on the ice?
That's a great question, and you're absolutely right about this. So we do not watch sea ice thickness mainly for the sea level bump, because as you mentioned, when the sea ice melts, it does not, adds a huge amount of water, which is enough to raise the level. Um, but I would add a little bit of, there was a research which was conducted, and there are not too many, but there are certain arguments which do talk about and suggest that sea ice melt in fresh water may not increase the sea level, while the ice which melts in the ocean, it may have a minuscule impact on the sea level. And that mainly can happen because it decreases the density of the salt water and it can raise the sea level slightly. So, having said that, while the effects may be minimal, as I mentioned, the floating bodies of ice still contribute to about 1.1 millimeters of sea level rise between 1994 to 2017. And that's why it's important to understand these changes accurately. So you are right when you said about the Archimedes principle that in fresh water, sea ice melting will not cause a tremendous change in the sea level, but there have been certain studies which have connected the melting of sea ice in the oceans to be causing a little bit, tiny bit of increase. So that's something which we cannot completely ignore it. So that's something which is also an important aspect. And it was one of the studies which were conducted here at NASA, which first brought it into consideration that there are certain changes which are taking place with that. So a quick sea level reality check is that only the ice that used to sit on the land, that is your glaciers and big ice sheets, they definitely raise the sea level directly when it melts into the ocean. Floating sea ice, floating ice shelves do not majorly cause the increase in the sea level rise, but there are studies which do talk about them adding a minimal amount of increase in the sea level because of the density changes it causes due to the melting in the ocean water.
But yeah, Tawqeer, that point about the Archimedes principle is a very good point, because I remember as a kid, uh, my grandfather, I mean, this, I must have been about 4 or 5 years old or something. And I remember that he had a glass full of water and with some ice cubes on it, and it was filled to the brim. And he was like, "You look at it, the ice is gonna melt and the water is not gonna spill." And I was like, "What are you saying? I mean, of course it's gonna spill," and it didn't. And you know, to a young child, that is like, "Oh wow, it's like magic." But it's
Yeah.
essentially the Archimedes principle in action.
Yeah.
Right.
So, but again, this is, just pure drinking water and ice from that pure drinking water. But again, in the wild, in the planet, there are, the oceans have differing densities of water all getting mixed around and stuff. Like that's what you said, right? That there is a minuscule change, because this is not just fresh water. There is water of, different chemistry and density and, salt concentrations that are there. So I think connecting this, could you tell us like what different forms of snow, ice, glacier, all these things are there, and what are the constituents that make them up? Because I think like there are a lot of differences in their properties, right? Physical and chemical, both.
Yes, true. So I'll put it in a very layman term, a very generic term for the audience to understand. So since we've been talking so much about sea ice is nothing but the ice which floats over the oceans all around the Antarctic or the Arctic. It's present over the ocean. So that is the sea ice. And it's basically the frozen ocean which keeps floating, and it's not like tethered or, anchored to the coastal areas. There are certain components of sea ice which are attached to the coast. We call it fast ice. Since we are talking about sea ice so much, I think it's important to first understand how sea ice is different from different other forms of ice, which the terms which keep coming across. So sea ice is nothing but the ice which floats over the oceans. And it's nothing but, again, something which is made out of frozen ocean water or sea water. It's mobile, it keeps drifting, and it's mainly saline in its composition. So that's exactly what is sea ice. So when you look at the map of Antarctic or the Arctic, the ice which you see sitting over the ocean around the continent is what is sea ice. And then sea ice has different parameters in which it is measured. It could be measured in terms of area, which we call the areal extent of the sea ice area. It could be the concentration, which is the percentage of ice, which we find in every pixel. Like that's how the satellite measure it. And then you have extents, and then you have thickness, the vertical column, you have the sea ice volume. So there are different parameters which can be used to measure sea ice. And then you have glacier ice, which the term we use quite often. Glacier ice is very different from sea ice. It's the ice which is present on the land. Glaciers can also be present at higher altitudes. Glaciers can also be considered as riverines, that the rivers, they freeze in the crevices of the mountain, and that's how the glaciers are formed. And the main component, what differentiate it, this besides its location, is its composition. They're made out of fresh water and they are not saline in nature. Then you would have come across the term called fast ice. Fast ice is again kind of sea ice, but it is attached or tethered to coastal areas, and that's why it is called fastened ice or fast ice. And fast ice is becoming very quite jazzy in research these days. A lot of people are getting interested into looking at fast ice because it's a new concept. Not a lot of data sets are present for fast ice as well. Models are not able to capture it really well. So that's a new interesting topic which is coming up in the cryospheric sciences. And then, of course, you would have heard about icebergs. And these icebergs are, again, nothing but these floating huge chunks of ice, which, could be drifted away from, it could be a portion of glacier or an ice shelf which broke out from the land, and now it is moving somewhere in the ocean. It's big enough to cause accidents like we saw in the Titanic. So that's iceberg. So these are like very general terms which keep coming across to us when we talk about polar areas and ice in general. So yeah, these are the different divisions. And what differentiates them is mainly where they are located and their composition.
So I'm gonna put my atmospheric scientist hat on for a moment and like ask you. So of course, I mean the Earth system is a, for lack of a better word, a coupled model. So any changes that are happening in the atmosphere affect the ice, the sea ice, and the cryosphere, and vice versa.
Mhm.
So I was just thinking that all this melting of sea ice and the reduction in like sea ice volume, how does it affect the atmosphere, or like does it lead to disruption of like some kind of wind systems or currents? Like, does it have any effect on the atmosphere really, or not? I'm sure it does, but like, what is the effect?
Yeah, I mean, absolutely. Whatever you said, the changes which take place are the combination of all those things which you talked about right now in your question. So, as Toki asked about the Archimedes principle, and my answer to that was that yes, the sea levels are not majorly impacted by the melting of the sea ice, but what it impacts is the whole feedback it has and the interactions it has with oceans and the atmosphere. So when I talk about the feedbacks, it changes. The first and the most prominent one, which comes up in my head, is the albedo feedback. So what happens is when these sea ice, which are chunks of ice floating over the ocean, as I mentioned, they start to melt. They expose the oceans which are underneath. And I would also want to introduce this term albedo to the audience. It's nothing but the reflective capacity, the how much of reflectance is present. So, for example, ice has a more reflective surface, so the albedo is high for the ice compared to water, which are darker surfaces where the reflectance is reduced. So there is a low reflectance or low albedo for the oceans or open water of any kind. So comparing those surfaces which are covered with ice with those which are not, the reflectance is what is different. So when the ice is removed, the ocean surface is exposed, the reflectance reduces, and the absorption of the heat from the atmosphere increases. So this in turn increases the heat component of the ocean, and this can cause or accelerate the sea ice to melt at a rate which is faster compared to that when the ice was covering the ocean. So it overall increases the temperatures in the polar areas. And as I said, and as you also correctly pointed out, that the sea ice melting in the pole is not a standalone phenomena which is happening and is only concentrated in the polar areas. Its impact resonates globally. There are extremes in the climate which will take place just because there is melting taking place in these polar areas. There is a thermohaline circulation, which is very conveniently balanced by these sea ice and the densities of the ocean waters. And a little shift can completely throw the system off. And when we saw movies of 2012 and all these thermohaline circulations being disrupted, at that point we thought that, oh, it was possible, but in future, when is it going to happen? But with these melting glaciers and sea ice, what we saw in the movies can actually come into reality, and that would not be a surprise. We don't know when, but it's not impossible. So, and at the same time, we'd also talked about, again, ecosystems being completely thrown out of balance. This can happen very easily just because we are melting a little bit too much of ice than we thought we were doing it before.
Okay, so Shreya, what exactly control the sea ice thickness in a given week or season? Is it mostly freezing and melting, or is it mainly because of winds and currents that pushing the ice around and changing its thickness?
Okay, yeah, great question, Touqeer. So here, since we are getting into the mechanisms of what and how the sea ice changes, since you talked about the changes in the sea ice over weeks and season, I would want to introduce two terms here to the audience, which is thermodynamic and dynamic. Again, I don't want to sound too jargony with whatever terms I'm using, but if we try to break it down in terms of sea ice, thermodynamic are the mechanisms which cause the change in the ice through temperature changes or thermal changes. So any melting or freezing of the sea ice is basically the thermodynamic changes which are happening here. The dynamic changes are those which are more like push and pull. They are more wind driven, ocean current driven. So they can cause the ice to break, converge, and diverge depending upon the regional wind configuration. And they can form a rubble and get very thick, or it can just spread it out and you see a very thin, flattened out sea ice. So those are the dynamic impacts which the winds and the currents they can have on sea ice. So these are the two sets of parameters which can cause the sea ice distribution to look the way they are. But having said that, thermodynamic and dynamic mechanisms are so closely intertwined to each other that separating them or demarcating them as saying that, oh, these are the thermodynamic impacts and these are the dynamic impacts, and pinpointing their exact contribution to how they would have caused the sea ice to change is still a challenge, and we are still working towards it. But yeah, in a nutshell, these are the two mechanisms which control the distribution of ice. And that's how we see it over the seasons and the weeks as well, as your question mentioned.
That's a great explanation. I had a follow-up question to that, which is that, I mean, you've been in your postdoc for not even a year, so I don't know if I should pose this question. Since we are reconnecting after almost a decade, I just wanted to ask you a question that is related to your journey in these last 10 years, which is that what basically was the meat of your PhD thesis and how that connects to your current job. So I know that you are working on sea ice thickness specifically, but on a day-to-day basis, what are you really doing? Are you testing models against observations? What kind of data sets are you looking at? What kind of numbers do you crunch? So it'll be nice if you could give like an overview of that. And what are the papers or preprints that you've written?
Okay, so I'm gonna take a couple of minutes from you just, to overhaul that in my head. It's been a long journey at UCLA. I will answer each of that question separately, starting first with what exactly I did at UCLA. So, as I mentioned initially too, it was all about sea ice, Antarctic, the sea ice and climate linkages. So that's the core of what I did. How I achieved that research was, or the data sets and the methods which I used for achieving that research in my at UCLA was, I would say, I got majorly heavily invested and interested in coupled climate models. I was fascinated. I remember there was this one course work which I had in my initial years of PhD, where one of my professors they introduced me to CMIP6, which are coupled climate models. And I really got interested in knowing that how the sea ice diagnostics or sea ice simulations look like in these coupled climate models. And from there, I started, my research was mainly concentrated and revolved around using climate models in understanding sea ice and sea ice changes and the sea ice and climate linkages in the Antarctic. So if you talk about the data sets, climate models were the first ones I looked at. And then I also looked at some reanalysis data sets. So reanalysis data sets are nothing but mostly the model data, which has been corrected using observational data sets. So they are better than models. They're closer to observation data sets, but they're not exactly the in situ data sets, but better. And then I also used a couple of satellite data sets. We'll talk about them a little bit later. So mainly it was radar altimetric missions, which measured sea ice thickness. That's what I used for my PhD thesis. So, so yes, models, reanalysis, and in situ satellite data sets were what I was completely, working on as a PhD student. And yeah, this was about the data sets I used. And then you said the research, right? Then once I had my, data set in place that this is what I'm going to use, my methodology was such that I wanted to then compare the performance of climate models in simulating sea ice by, putting them alongside these reanalysis and observation data sets. So that was what I did. That was one of the aspect, a comparative study. Then my second component was, once I had the comparative study in place, that how these climate models can be used for understanding the sea ice and climate linkages. So that was what I did for my PhD. I had some really interesting results which came up from my PhD papers, which are currently under review. And one of those papers, one of the findings I had was what I proposed as a part of my proposal here at NASA Goddard, as a part of NASA postdoctoral program. And they really liked that result. And I also proposed how I would want to expand on those results. And that's how I got my postdoc position here.
Well, I mean, it's been a long time that I also did kicked around a bit in the field of cryospheric sciences. And if you remember, I mean, we guys were together in our internship during our masters at National
Yeah,
Institute of Hydrology in Roorkee. It's a city in India for all those people who don't know where Roorkee is. So I think both of us were working that time on Himalayan glaciers, right?
right.
And we used a lot of optical data sets, I think Landsat mainly. That time, I don't think we were using any microwave imagery, if I remember correctly.
Yeah, right.
So now in your like current work, you basically use a lot of satellite data sets. But I'm sure that you also need a lot of in situ data for validation purposes and stuff. So like generally in CIS research, what is like the contribution of satellite data sets and in situ data sets in research? And are there like people who take ice breaking ships and do probably circumnavigation of these areas to get in situ data?
Right.
Because I can imagine satellite data is they are just taking snapshots of the planet every day. But I'm actually more interested in like the in situ data part of it, because I mean there are scientists who are probably away from home and family for months at a time trying to collect this data.
Yeah, no, that's a great question. And it also brings me to, elaborating on different tools which are used for measuring sea ice thickness. So, as I mentioned initially, to a little bit about how sea ice concentration and its derivatives of area and extent are easy, relatively easy, and more reliable data sets which are available these days, and they're easier to get also. They're more passive microwave based ones. For sea ice thickness, there are a variety of tools which are used, starting with the satellite component. Since I have mostly worked with the radar altimeters, and to give an example, I would say Cryosat 2 and NVSat are like the ESA or the European Space Agency based satellites which have been used for collecting the freeboard data of sea ice, and that's something which is converted into sea ice thickness. So radar and laser altimeters are the two most important methods which are used for getting the freeboard or the sea ice thickness. I can talk more about the radar part because I've used it. For the laser, I have recently started working as a part of NASA. So I would say that my knowledge is very limited in that case. But for the radar, I can explain that how that works. So what's happening here is that imagine sea ice as a floating raft on a snow blanket, right? There's a huge chunk of sea ice which is floating in. And when I talk about sea ice, it's not just the ice which floats on ocean. There's also precipitation and snowfall which is taking place. So there is a big blanket of snow which rests very conveniently on that block of sea ice, right? So when we try to measure the thickness of the sea ice, we have to also take into account or basically try to delete that component of snow layer which lies on the top of the sea ice. And that's where the problem comes. Because when we use these radar altimeters and satellites like Cryosat and Envisat, they measure the freeboard, which is the ice floating on the ocean. It strikes the snow and sea ice interface. And this interface is where the problem starts. Because if the radar is not able to get that exact interface of where the snow is ending and where the sea ice is starting, it will result in huge errors in freeboard. And once we get this freeboard is further put into some hydrostatic equations, and these equations calculate sea ice thickness using the freeboard value. And if the freeboard values come with errors, these errors get amplified when converting them to sea ice thickness. So, as I said about the reliability part, the radar altimeters, they give you a lot of errors because they are not able to assess the correct sea ice and snow interface, which leads to exaggerated errors when it comes to thickness calculation. These errors are reduced for the laser altimeters, which have a relatively better resolution because what they measure is the surface height, and usually they see the top of the snow on the sea ice. So they give you a very crisp freeboard, and then that freeboard can be put into the hydrostatic equilibrium equations, and then the sea ice thickness can be obtained out of it. So the research have put the comparison into sense that the laser altimeters, they perform relatively better than the radar ones when it comes to the accuracy and reliability of the data. So these are the two major types of altimeters which give us information on how the sea ice thickness is calculated. And since you mentioned that you're more interested in the in situ measurements, there are several too, actually. And the first one being the ice mass balance buoys. So these buoys are the instruments which are attached to these ships, and these vessels are left floating in the ocean and with buoys floating along with them, and they just collect information about the freeboard. And then, that's exactly what happened in the Mosaic mission also in the Arctic. And I think the name of the instrument was Polarstein. I don't remember, like, correct me if I'm wrong. But for the Mosaic, it was left in there for a good 1 year period. And then the data which was collected as a part of Mosaic was pretty good. So, and a lot of studies have also been done in that case too. But the story is very different for the Antarctic. In the Antarctic, the ship vessels are, however, limited to summer seasons and only in those areas where sea ice is thin enough for the passage of vessel. Therefore, there is a gap in the reliable sea ice thickness data for the winter season, and also certain areas where there are thick multi-year ice which persists. The vessels are not able to penetrate through them, and there are huge gaps in sea ice in those areas too. So yeah, that's one of the problems which we have for sea ice thickness data collection in the Antarctic. We also have the upward looking sonars, the ULS moorings, which are present. Of course, they have been employed in quite different regions in the Antarctic, but again, the data is quite sparse. And then the whole drilling and getting the ice cores due to ice core drilling is also present. But again, all these come with complications. The weather and the climate there is extremely harsh for people to collect good, reliable data. And also, that is the reason why there we have temporal and seasonal blockages because of a lot of challenges which persist in these areas. So, yeah, in a nutshell, all these are the tools and instruments which we use for sea ice thickness.
Okay, very good and very detailed explanation, Shreya. So now I have a very one simple question here for you. If 10 extra Bausi drops into your lab tomorrow, where would you put them first and why those places?
Yeah, that's a very interesting question, Touqeer. And if hypothetically that happens, I would like to split them between gateways and blind spots. So gateways are basically the places where winds, currents, and gyres they reshape the ice pack. In the Antarctic, I would say those regions are the Weddell Sea, where the most of the multi-year thick sea ice persists, and maybe I would say the Ross Sea as well. And then the blind spots are the regions which are hard to reach in winter, but for the matter of circulation and habitat, they are important hotspots. So in that case, Bellingshausen and Amundsen seas maybe. So, and maybe if I would drop a few buoys here and there too, just to get a good sense of different sites and how the thickness changes are taking place all around the Antarctic. But yeah, in a nutshell, that's how I would want to hypothetically place those 10 buoys which fall in my lap tomorrow. I hope that happens. It'd be so cool if I could do that.
I mean,
But
what's your beef with the Arctic region? You can drop a couple of them near Finland and Norway, this area as well.
Yeah.
Arctic already has an advantage. Come on, you guys. Like, I see. And also, being a researcher who works in the Antarctic region, we are always a minority. Whenever we go to these cryospheric conferences, there are people working in the Arctic. And then I'll be the only meek one saying that, oh, I'm with the Antarctic. And I am even, I get more into the minority part when I utter sea ice thickness because no one wants to touch sea ice thickness. So Arctic people already have enough.
Yeah, I
So
mean, it makes
we need more
sense
strength
that
here.
most of humanity is located in the northern hemisphere as well. So,
Exactly. Yeah, that's true. That's why we need more buoys to be dropped in our lab. Not tomorrow, but today itself.
So, Shreya, you have been testing models against observations. So, do the models get thickness right in the places and the season that matters most?
Oh, thank you for the question. And that actually brings me to explaining what exactly I've been doing as the part of one of my preprints, which I've recently submitted. So, in my research, as I said, it was a comparative study of climate models with different data sets of sea ice thickness. I used some 40 SIMIPSITS models against the satellite-based thickness products and the reanalyses. Since the observations are not really that great as of now for the Antarctic, but the good news is that with whatever data set which we have for this sea ice thickness, models are able to capture the broader seasonal cycle and the large scale patterns. And that's a good news is because it's a great place to begin with. With the limited data which we have and models being able to capture at least a little bit of it is a good news because models can provide us an extended spatial and temporal resolution for us to make um, some detailed studies where sea ice thickness can be used. So, what I specifically found in my research was that models they tend to match satellite products better in the late summer around February, and that was something which we found unanimously, like across all the 40 models. They were able to get the February data point correct. But what was happening again was that once we progressed into the early spring and September, this alignment of the models shifted more towards the reanalysis product. So we do at different point in the year have some sort of alignment of these climate models with either satellites or the reanalysis products. So although A complete alignment was something which we missed in the models, but the seasonal alignment was something which we found across all the 41s which we used. And that I would say was a good result. And I was very happy about it. So, yeah, that was one of the findings. And there was another very interesting find which we saw was when we started comparing sea ice thickness and sea ice area. And that's something which has not been done before. We have done it for the very first time in our paper, that we looked at the signals, correlation signals between thickness and area, and we found a seasonal covariance between them. And what exactly is that? For example, in September, which is the austral winters, when there's winter in southern hemisphere, area and thickness, they co-varied positively. So when one was increasing, the other was increasing too. And that's expected, that is possible, that's going to happen because once the temperatures they start to drop in the winters, there is greater sea ice freezing. So there will be a gradual increase in the thickening part of it because the ice will start to get thicker in response to the lower temperatures. And at the same time, the areas will also start to expand. So there is a positive covariance, which I said was seen in the winter part. Then in February, once the season changed, and this is the austral summers, the melt season begins. And what happens is that the area starts to shrink, of course, and that's going to happen because the temperatures are increasing. But the thickness stays quite high in those areas where the multi-year ice remains. So there was a negative correlation which was seen in the month of February. And of course, the reason is what I told you, that it was only the thickest of the ice that survived the melt season, and hence the thickest ice remained, and the area was shrunk to the minimum it could have for the month of February. So these two were the two results which we had in our paper. And they were quite interesting because that also happens to be one of the first researches which have been done using coupled climate models and how the thickness simulations look like in them for the Antarctic.
So, Shreya, you have convinced us that sea ice thickness matters, and a lot of people, I'm sure our listeners, have looked at those pretty maps of Antarctica that show, the ice extends across different years and decades with, nice color shading in atlases and stuff. So I was just thinking that how would you connect the area or the concentration to thickness and uh, show how that gives the volume? Because I guess the volume is also a very important parameter for sea ice research. And also,
Absolutely.
did you find
Yeah.
any other patterns that tell us the same story of seasonal covariance, which you would like to share, as you mentioned, that there was some interesting finding during your PhD thesis, which you sort of extended as part of your NASA postdoctoral proposal?
Yeah. Thank you. Yes. First, I would like to take up that question regarding the volume, and thank you, Sujai, for bringing that into focus. Because, yes, I'm glad that I convinced you about the sea ice thickness. Sea ice thickness is the ultimate game changer when it comes to understanding the absolute sea ice changes in the Antarctic or in the Arctic for that matter. Because, as I said, that most of the studies have concentrated upon the surface parameters, understanding or basically putting the sea ice thickness into the research will give us sea ice volume, which is nothing but a product of area and thickness, and that will give us an absolute change in the sea ice. So it's not just the surface or the peripheral changes which we are looking at. Yes, we are interested in it, but we also want to know the absolute amount of the ice which gets melted out or is being added. And for that, we need volume, right? So thickness will provide us volume. And that is why it's very important, at least now, for us to know the sea ice thickness measurements. And yes, glad you reminded me about that interesting finding which I was talking about. And that interesting finding is what I would love to call thickness dipole. Thickness dipole was one of those interesting phenomena which we noticed in one of the researches we had. Since I mentioned about the covariances between area and thickness, these thickness dipoles were the regions where there was thickening taking place in one part of the Antarctic, and at the same time, in its neighboring region, there was thinning which is taking place. So it was like regions of thicker ice and thinner ice coinciding and, lying side by side to each other. And that's what I wanted to, like, I chose to call as thickness dipole. And that was just a phenomena which we saw in the research. And yes, that was interesting. And I wanted to know why exactly that is happening. And that's something which I am pursuing as a part of my postdoc research at NASA. So yeah, it was like that sea ice was responding in different ways to the same set of climate drivers, and that was fascinating. And yeah, we believe that it was mainly because of the dynamic factors which were playing a dominant roles in dictating the sea ice thickness patterns. So yeah, it again brings me to reiterate the point that if we only watch area or concentration or extent, such patterns can just hide in plain sight, and involving thickness and volume, it reveals it directly, bringing me back to how important it is to have sea ice thickness component being incorporated into the cryosphere studies in the Arctic as well as in the Antarctic.
Okay, so thank you so much, Shreya, for this much detailed answer. So, what I understand until now is that this scorecard is very simple. Volume is the number we really care about, and to get the volume, we need thickness. And winter is still where the thickness is blind in too many places. So, your work actually fill that gap with smart anchors and the better checks, right?
Exactly. Yes. So as I mentioned that the maps of extent and the fields of concentration are extremely useful, and 90 to 95% of the research which have been conducted in the polar areas has concentrated mainly on these parameters. But we cannot deny how important thickness is. And of course, volume is the climate currency because it tells us how much ice is in the bank. It tells us the absolute changes which are taking place in the polar areas. So the modeling work and the preprint which I have, it shows that we can read that currency better. And if we fix the snow ice representation, the snow ice interface errors in the satellites, the understand the dynamic and the thermodynamic mechanisms and how they dictate the sea ice patterns, the ridging, the ice edge physics, and also tweak a little bit how climate models they simulate the sea ice. I think we will get closer to, understanding a little bit more about how the sea ice absolute changes are looking in the polar areas. And of course, we'll also improve the global climate models and the satellites too. So, yeah, we're getting there. And I think we have come a long way as well.
So, with that, it's a wrap, and I'll pull your leg a little bit. So, I'm not going to call you Shreya now. Dr. Trivedi, thank you very much for the masterclass. It was really an eye-opening episode. I know that this research is a very difficult field because there is like so much modeling and there's so much data analysis, and then in situ measurements are a complete other ballgame altogether. So it's really interesting the work that you are doing at NASA Goddard. And also today we are recording, this is the 13th of November, an interesting time because COP30 has just started.
Yeah,
It is at Belém in Brazil.
Brazil.
So COP30, I think, started on 10th November. So it's been a couple of days, and I see that a
Yes.
lot of indigenous people have been protesting, and I think they even clashed with the police in Brazil. So we are talking about the right things at the right time. And I hope that politicians and especially the political class in your country really listen to what scientists have to say. And I think just a couple of weeks back, Dr. James Hansen, who headed Goddard Institute of Space Studies, that is GISS in New York City, he was here in Finland to deliver a talk. So it's nice to see that at least a lot of concerned American scientists are coming to Europe and raising their voice
Yeah.
about climate change and what climate scientists ought to do.
Right.
So thank you very much, and please like, share, and subscribe our podcast episodes with your friends and family. We are all on your favorite podcast platforms such as SoundCloud, Spotify, and Apple Podcasts. And now we are also on YouTube, but only in the audio version. so you won't be able to see us. And for past episodes, you can also check out our website, thesciencebasement.org. So thank you everyone for tuning in. Thank you everyone for listening. And until next time, take care and bye.
Thank you, Touqeer and Sujai, for having me. This was an absolute fun, and I was very excited to be a part of this. And I'm eagerly waiting for those 10 buoys you promised to drop on my lap tomorrow. So please let that happen. And yeah, and thanks for calling me doctor. It just still sounds a bit iggy piggy for me because I've been very freshly graduated. But yeah, it feels great. And as I said, that it was a very good experience sharing my research. And I think this podcast is a great way of providing avenues to early career researchers like me to share my work with more interested people who would be interested in the work which we are doing. So thanks a lot for having me, and goodbye then.
And thank you so much, Shreya, once again, for making sea ice thickness feel like something we can actually measure and trust, even when the weather is not in our favor. So, once again, thank you so much, and bye bye.
Bye.
The Science Basement.